In this lecture, we will start with Runge-Kutta method of fourth order. This method is also known as RK method of fourth order. For your information, we already have studied such kind of methods earlier. The first method was Euler's method, which was known as RK method of first order. Modified Euler's method, which is also known as RK method of second order. And Runge's method or Runge's method is RK method of third order, while we are directly going to Runge-Kutta or Runge-Kutta method of fourth order. Obviously, the other three methods are nothing but, we can say, a prior version of this method, and hence this Runge-Kutta method of fourth order is much more advanced method. It will give you very good output as compared to the previous methods. We will just sum up all the expressions coming out from the simplest procedure through Taylor's series expansion, and we are not going into the details of deriving all these expressions because we have seen much more these things in detail while discussing Euler's method. So let's see, by not wasting our time, the first k1, this factor is nothing but h times this slope f into x naught y naught, and k2 is another factor, that is h into f x naught plus h by 2 y naught plus k1 by 2. k3 will be h into f x naught plus h by 2 y naught plus k2 by 2, and k4 will be h times f x naught plus h and y naught plus k3. Basically all these expressions are interrelated and we are going to use the previous expression at the moment. For example, the second expression k2 can be obtained by using k1 from the earlier expression. In the same way, k3 can be obtained by using k2, k4 can be obtained by using k3, and finally k has another relation which is nothing but the relation depending upon all these ki's which I have written here. So basically k is weighted mean of all these ki's, and the expression which you need to remember here is this one: k is equal to 1 by 6 k1 plus 2k2 plus 2k3 plus k4, right? So basically if you remember this expression, then you are through for Runge-Kutta method of fourth order. Okay, and hence the required approximation will be y1 equal to y0 plus k. Now let's see an implementation through an illustration. Apply Runge-Kutta method of fourth order to find an approximate value of y when x is equal to 0.2, given that this derivative dy by dx is equal to x plus y, and y is equal to 1 when x equal to 0. Basically this y is equal to 1 is nothing but your initial approximation. You are asked to find the value of y when x is equal to 0.2. Okay, so let's see that how do we proceed for the solution using this method. Here just we are writing all the informations that we are already having from the statement. So x naught is 0, y naught is 1, h is equal to 0.2. Directly you are jumping from 0 to 0.2, and f at x naught y naught is 1, and that can be obtained or observed from this relation x plus y, right? Okay, now let's see one by one expression. K1 from the earlier expression h into f of x naught y naught that we have seen, just substitute the values which we have on hand. H is 0.2, f x naught y naught is 1, that is nothing but this 0 plus 1, okay, and hence 0.2 times 1, that is 0.2. Similarly, k2 is h times f x naught plus h by 2 y naught plus k by 2, that is 0.2 times f evaluated at this one 0.1 1.1. Basically we are just using the relations here, x naught plus h by 2 y naught plus k1 by 2, and k1 by 2 is nothing but 0.2 divided by 2, that is 0.1, and y naught is nothing but 1, so 1 plus 0.1, that is 1.1, and x naught plus h by 2, x naught is 0, h is 0.2, so 0.2 divided by 2, that is 0.1. Now what is this? This is nothing but you are seeing here x plus y, so just substitute x is equal to 0.1 and y is equal to 1.1 to get the value of this function, and then multiply it with 0.2 you will get 0.2400. Fine. I hope you have got this idea that how to find K2. Okay, next is go back to the expressions that we have studied and just recall that what was the value of K3? That is nothing but this one. K3 is equal to H times F x naught plus H by 2 y naught plus K2 by 2, right? So you are familiar with this one. H is nothing but 0.2 and x naught is 0, H by 2, H is 0.2, so 0.2 by 2, that is 0.1, and again x naught is there, and similarly K2 is there. K2 is 0.2400, so K2 divided by 2, and then add it y naught, and then finally substitute it to and simplify it to get this answer. So that answer is 0.2440. You can just pause the video, work out this thing and cross check it whether you are getting this value or not, right? And K4, now the turn for K4. K4 has not, just recall those expressions, it has not division by 2 format here, and similarly here. So here K4 is equal to H times F x naught plus H y naught plus K3, which is 0.2888. And finally, once you obtain these all values K0, K1, K2, K3 and K4, then you are having readily available these all values to find K. So based upon these all values that you obtained just now, the value of K will be 0.2428, right? And once you have obtained this value K, you can substitute here to get the desired approximation. So here y1 is y naught plus K, that is 1 plus 0.2428, which is equal to 1.2428, right? The above value gives required answer for a single step. But what if we have to go for a multi-steps? See, basically, what do we mean by single step and multi-step? From the statement, if you recall, we are given x equal to 0 and we are asked to find the value at 0.2 when x is equal to 0.2, right? So without even further thinking, we straightforward took out the value of h as 0.2, right? And hence this was only a single step. You have directly jumped from 0 to 0.2. But what if in question you are asked to go with smaller jumps, like you need to go with 0 to 0.1 and then 0.1 to 0.2. Okay, so that is the thing that I am going to mention here, that what if you want to go with multi steps. Let's see how to get through such case. However, we will just discuss the overview of the method rather to solve the problem fully, but it makes sense to understand thorough. So if you are given such kind of problem where you have to apply RK method to find the approximate value of y for x equal to 0.2 in steps of 0.1, just notice this thing. If dy by dx is some function x plus y square, given that y is equal to 1 when x equal to 0. So I am just going to give you hint here. Stage 1, that is you are starting from 0 and you will reach to x is equal to 0.1 by using step size h is equal to 0.1, right? So just apply normal RK method that we have seen in the previous problem and your answer will be 1.1165, but please keep in mind that this answer is pertaining to the value of x equal to 0.1, and now your target is to find the value of y when x is equal to 0.2. So you will again use this thing in your stage 2. So now your x1 is x naught plus h is 0.1. So your x1 will be 0.1. Initially it was 0. Now your x1, that is new step, 0.1. y1 already you have found here and that is 1.1165. Again h is 0.1. So that h can be used to find out successive values for k1, k2, k3, k4, k, and then y2 will be y1 plus k. I mean, you have obtained now this value by using one more step here, right? And hence using this thing, now you could obtain y at 0.2, which is equal to 1.2736. You can check this out, and by in this way you can even go for multi-stage processes, right? So I hope with this video you will have a clear idea that how to implement Runge-Kutta method of fourth order for any kind of first order differential equations using initial approximations. and you can make sure that the answer which is obtained through this method will be much more greater in accuracy as compared to all the previous methods like Euler's method or modified Euler's method or even Runge method itself, that is nothing but of third order, right? So thank you very much. Once again, I just request all of you to go through the video and try to understand these expressions, try to remember these expressions. It will be much more helpful in solving such kind of problems. Even in GATE exam, this method is very important and it will be surely coming into some kind of problems when you want to solve on the basis of numerical analysis. So thanks a lot. We will see some more topics, interesting topics in next video lecture. Thank you everyone.